Lesson 24, Velocity and Acceleration. All right, so by the end of this lesson, you're going to be able to find the first derivative of a position time function to find instantaneous velocity. And then you'll be able to find the second derivative of a position time function to find instantaneous acceleration. So you'll probably see where we're going with this. We're going to be applying derivatives to physics, really, right? So we're going to be able to find, if we have some position time function, we'll be able to take the derivative of that to find velocity and the second derivative to find acceleration, right? All right. So if you recall, velocity is just a change in distance over a change in time, which makes sense because the units are meters per second, right? And if we graph this, then if we had a linear relation like this, then it would really be the slope of the graph, right? That would be your velocity, right? The rise and the run there. Okay, so if we use that, then if a function is nonlinear, right? So if we were dealing with something like, so distance and time, and then we have a situation maybe like this, then we can find the average velocity by finding the slope of the secant line between 2 points. Now, if you remember what a secant line was, it was if you took any 2 points on this graph and connected them, right? So if you had a straight line between those, then the slope of that secant line would be the average velocity between, let's say, this time, if that was like time 1 second, and this was, a time of like 4 seconds, right? Then we can find the average velocity in that time frame. Okay? Now, you probably see where we're going with this, right? Because we've done this before, right? When we start bringing those points ever closer to each other, well then, yeah, I'm kind of getting ahead of myself. But first off, let's figure out what the average speed is, or average velocity, in this case, because they're both positive, there's no direction, of this function, right? Between the intervals of 4 and 6. Okay, so if we were going to do that, then we'd say, well, the average velocity, so V average, will just be my change in distance over a change in time. Okay, so then a way of writing this for distance, right? That's my y values in this case. So you could say that that was d6, right? So the distance at 6 seconds, okay, minus the distance at 4 seconds over, and then 6 minus 4. Okay, so you can when you find the distance at 6 seconds, you just be plugging 6 into that. I won't do that step. You'd end up getting, what ends up being 535 minus 235 over 6 minus 4. And then that comes out to 150 meters per second. All right, so now instantaneous velocities. So the instantaneous velocity is the velocity at any given time, right? So again, if we were to graph this thing quickly, then when I'm talking instantaneous velocity, I'm talking, let's say right here, right? Maybe this was 3 seconds. So what would the speed be right at that point? And again, you can see, well, we'd like to bring those points, those of the secant line, closer and closer together, so that we're just looking at the speed right there. And if you guys have taken physics, then you probably were able to figure out the instantaneous velocity by just kind of doing it on a chart and then figuring out the rise and the run, right? Now that we know calculus, we can use limits to do that. And in this case, it's going to be, well, derivatives again, right? But it really would be the limit in this case, right? So the velocity at any given point, so f prime of t, then we can use the limit as h approaches 0, right? So this is like the distance between those 2 points again, if you remember way back, right? So we're bringing that distance down, okay, down to 0. And then, well, this really is the derivative, right? Those are our first principles. So that would give us the slope at that point, the slope of the tangent line at that point right there, right? So that's the idea. And then you guys know we don't really need to use first principles every time we find derivatives anymore, right? Luckily, we know how to find derivatives. So let's kind of jump into it. We're just really going to be finding the derivatives of these things and then interpreting the meaning. So to determine the velocity of a function, we take the derivative of the position function, since velocity is the rate of change of position. Okay, so now this one says find the velocity of the function d of t is equal to 35t plus 8 at t is equal to 3. Okay, so a time of equal to 3. So let's find the derivative of that. So the derivatives of dt is equal to, and well, if I take the derivative of that, right, that's just equal to 35. So, okay, the derivative at 3 seconds would just be, well, it seems like it's always 35, doesn't it? And let's just check to make sure that makes sense. If we graph this linear relation, right, this would have a y-intercept at like 8, and then it, will go up to the slope of 35. Then if I'm saying at like 3 seconds, what's the slope? And we figured out it's 35, well, yeah, that makes sense on a straight line, doesn't it? The slope is the same everywhere. It wouldn't matter what time we threw into that, right? Because we're dealing with a straight line. So that makes sense, okay? Okay, next example. The height of a baseball after t seconds is defined by the function yada, where t is the time in seconds and h is the height in meters. Okay, before we get going, actually, I want to show you, if you guys have taken physics, just a connection here, right? Maybe this looks a little bit familiar, maybe it doesn't. We were dealing with this a lot in Physics 20. So does this look familiar at all? So the formula D is equal to VIT plus 1/2 AT squared. Okay, so this 30 here looks like that was my initial velocity in this question. The A is 9.81, and more correctly, it's negative 9.81. So that'd be like negative 9.81 divided by 2. That's where we get the negative 4.9, right? So again, I just want you guys to see the connection between physics and calculus. They come up a lot. But, all right. So now, determine an expression for the velocity of the baseball at t seconds. Okay, so this was our expression for the position or the height at any given point or at any given time. So if we want to figure out the velocity, then we want the slope at any given point. So again, I like graphs. So they help me. So this graph, would do something like this, right? We know that it's going to be opening down like that. It's a parabola. Yeah, so something like this, right? So now they're saying what's the velocity at any given point. So really, we want to know what the slope is at any given point. Maybe at the top, maybe on the sides, right? Whatever it is. But we want just a general equation that I can just plug in time for any place on this graph, and it'll give me the velocity, right? So let's derive an equation for the velocity of the ball at any given point. So take the derivative. Now, we'll say V is equal to your change in height over your change in time, right? Like that, just in general, that's what we know, right? So when we take the derivative of this, you guys we did a bit of this before. We'd say dH dt. And this is a helpful way to write it, especially in the physics context, because we can see that we're talking about a change in height over a change in time. And the way we'd say this is it's the derivative of h with respect to t. And when I say with respect, we're really just saying the thing that's changing, right? So with respect just means that t is like our x-axis. So it's t is what's changing, and height would be height is the one, like, dh dt, which is really v, right? Going up and down. So, okay, so anyway, with respect to is your time, right? Okay, so we'll say dh dt, which is equal to v. Okay, we also just write that in there if we want to, because that is the velocity. The derivative of the height with respect to time is the velocity, right? Okay, so if we do that, we'll just derive this one. You guys will be good at this. So this is 30 minus 9.8t. Okay, and there you go. There is our equation for the velocity at any given point on that graph, right? Again, in the physics contest, this should look familiar too. Think of this one. Vf is equal to Vi minus At, right? Or rearranging that, plus At would be, right? So then rearranging that, you'd have, that'd be the same thing from your formula sheet back in Physics 20. Vf minus Vi over T is equal to A. Yeah? So same thing. We're fine. Like this is like the fundamental way that these equations were derived, right? Okay. So now determine the instantaneous velocity at 2 seconds. Well, that would just be throwing in 2 in for that, right? So we can say dH dt, or which is the same thing as V, at 2 seconds is going to be equal to 30 minus 9.8 times 2, which is equal to 10.4 meters per second. Okay, was the velocity of the ball, or when is the velocity of the ball 0 meters per second? Okay, so in this case, well, this was our equation, right? So V is equal to 30 minus 9.8 T, right? So now, when is it 0 meters per second? So that means I need to change my V to 0. So this will be 0 is equal to 30 minus 9.8 T. Whoop, T. Okay, so we get 9.8 T is equal to 30. So T is equal to 3.06 seconds. Determine the time and velocity of the ball when it strikes the ground. Okay, so when it strikes the ground, well, in this case, I'm going to be wanting to use the original function, right? When it strikes the ground, you can see from there, dt is equal to 30 minus 4.9 t squared. Okay, so when it hits the ground, well, this is my height, right? So this is the one I want to set to 0. Okay, so we'll set this equal to 0. And we'll factor out a t in the first one, right? So this would be t times 30 minus 4.9 t. Now, if we look at this for a second, this part makes sense, doesn't it? This is saying that t would be equal to 0. T would be equal to 0 here, right? At a time of 0. So again, if we graph this really just means it starts from the origin, goes up, and then comes back down again. That makes sense. It was at 0 to begin with, right? So that one makes sense. Now we just have to figure out this one. So this would be, I'll make my own little equation here. So we'll say 0 is equal to 30 minus 4.9t, and then solving for t there, I think you guys can do that, 6.12 seconds. Okay, so those are my 2 times, right? Now that we have those 2 times, then if we want to figure out the velocity, well, we just throw those times into our new velocity formula. Okay, so that's our formula for velocity. So for velocity, we're gonna just plug it in. So that would be v of 0. So the velocity at 0 would be 30 minus 9.8 times 0. Okay, so that's just going to be, so v of 0 would be 30 meters per second. Okay, so that's how fast it starts, right? It's going up at 30 meters per second. Now, v of 6.12. So if you plug that one in, we end up getting, well, negative 30 meters per second. And you can try that out if you like. I'm sure you guys can do that part too. Just plugging 6.12 in for t there, right? So doesn't this make sense? Again, with the physics perspective, it has the same speed going up to begin with as it does right before it hits the ground. Conservation of energy, right? Okay, next one. So yeah, just remember velocity is a vector, which means that it has a direction to it as well, right? So the fact that this was 30 and this was negative 30, that matters, right? All right, so next one. The position function of a particle is s is equal to all of this, where t is greater than or equal to 0, where t is measured in seconds and s in meters. Now this is kind of a funny one because we never did this in physics, did we? But in calculus, distance is quite often used with the symbol s. Okay. I'm not exactly sure why, but I have a feeling it's because writing, if it would have been d, right? Writing dd over dt is a little awkward, right? It's better to like think about this thing as being like ds over dt, right? You can kind of see more clearly that the d's were kind of like our change in symbols, you know. But yeah, so I think it's just to avoid confusion in calculus. Okay, so either way, we've got kind of a funny situation here, right? We've got a cubic function going on, so it's not going to behave like a standard parabola like in the last one, right? So in this case, when is the particle at rest? So, okay, we can figure out when it's at rest when the velocity is equal to 0. Okay, so step number 1, I got to figure out an equation for the velocity of this function, which means I got to take the derivative. So let's find, so v, which would just be equal to ds dt, derivative of s with respect to t, which is equal to, and then the derivative of this would just be 6t squared minus 24t plus 18. Okay, so now looks like we'll set it to 0. And at the same time, why don't we factor this, make it look a bit nicer too. So 6 is common to all of these, so I'll factor a 6 out. So 6t squared minus 24t, oh sorry, not 24 now, minus 4t plus 3. Okay, and then we'll just factor. And we get t minus 3 and t minus 1 for our factors there. So then this is going to happen at t is equal to 3 seconds and 1 second. When is the velocity negative and when is the velocity positive? Now, thinking in the last unit there, when is it positive and when is it negative? All right, so just for a second, we've got like a cubic function. I don't really know what's going on yet, but let's say it does something like this, right? Starting low, ending high. When is it positive and when is it negative? Isn't this really saying areas of increase and areas of decrease, right? Like when is the derivative, when is the slope of the tangent positive, and when is the slope of the tangent negative, right? When is it positive and when is it negative? That's really what's being asked here, right? So, okay, we're going to do a method similar to what we did in the last unit then. So, what I'm going to do, I'm going to make a number line. I like the number line method. You could use the chart method here too if you prefer that one. Okay, and I'm going to write down my critical numbers here, right? So this would be at 1 second, and then at 3 seconds. And I'm going to write down my equation for velocity. I'm going to write it in this form. I'll say v was equal to 6 times t minus 3, and then t minus 1, right? Oh. Okay. This form's nice, like the factor form's nice, is because I can kind of look at these parts independently now, too, to figure out whether the thing's going to be positive or negative, right? So let's throw in 0, right? Let's throw in, we'll check the value 0 for this section to see what comes out. So here, I'll say the velocity 2 to remind myself here. So when it's 0, then if I threw 0 into this would be coming out negative. This would be coming out negative, right? So 2 negatives, that means it's going to be positive in this section. So positive velocity before a time of 1 second, right? And to tell you the truth, I've got this arrow going all the way to negative infinity there, but really, we started at a time of 0, so that's what I really care about. So it's positive from a time of 0 to a time of 1 second, okay? Then moving over from 1 to 3, so I'll throw 2 in there. So if I threw 2 into this function, then that's going to be, well, 2 minus 3, so that's coming out negative. And then 2 minus 1, that's coming out positive, so it's going to be negative in this section. And then after 3, thinking they're both going to be positive, right? So that thing's coming out positive for sure. And then there you go. So there's our areas of increase and our areas of decrease. So I kind of cheated. I already kind of knew like a little bit what it was like. All right, so let's write this out now. We'll say that the velocity, so v is positive on the interval of 0, it'll be including 0, because we did start at 0, right? So time 0 does count, and it was positive even at 0 there, okay? It was moving at that point already, right? It didn't start from rest, which is a common mistake. Okay, so anyway, so from 0 to 1, but not including 1, because at 1 it stopped, right? Those are our 2 points that the thing stopped moving, right? It's at rest at 1 and 3, so it doesn't include that. It doesn't have a positive velocity because it's not moving at all at that point. So anyway, so 0 to 1, unioned with, and then same thing for 3, doesn't include it, and then to infinity. Okay, and then v is negative from, well, in between 1 and 3. Okay. Draw a diagram to illustrate the motion of the particle from 0 to 5. Okay, so let's do a rough sketch. So we'll say, so this will be distance time still. It'll be helpful to draw in our numbers here for 1 and 3, because we know this is where our graph is either going to come to a peak or come to a min, right? Okay, so yeah, those are our numbers. So what we're going to have to figure out here then is kind of, when I throw in 1 and 3, what are the distances associated with those positions, right? So let's figure those out. So for a time at 0, 1, 3, and then we'll do 5 as well, because it's from 0 to 5, right? And that should give us a pretty good picture of what's happening here. So if we plug them into the original equation, right, into the original, then s of 1, s of 0, let's do them in order. S of 0 would be equal to 0, which makes sense. That's our y-intercept, right? Okay, so we have a point right here. Okay, s of 1 would come out as, maybe I'll show you what that would look like too. So that'd be like 2 times 1 cubed minus 12 times 1 squared plus 18 times 1, and that comes out as 8. All right, so at 1, it's coming out as 8. So let's say 8's around there. And then we'll throw in s of 3, and that comes out as 0. So at 3 seconds comes out as 0. And then s of 5 comes out at 40. All right. So then, yeah, so 5, I didn't write it on there. Okay, so 40, so yeah, it'd be like way up here. Higher, but yeah, good enough. Okay, so then in the end here, we know that, well, okay, so it's starting here. It's increasing in this section. We figured that out before. Must come to a max here, right? We knew that the velocity was 0 at that point. Okay, so then it comes back down. And then same here, we knew that this was a min, right at 0. And then goes up to 5. So that would be in that section there. Okay, what is the total distance traveled from 0 to 5 seconds? Okay, so now notice the keyword distance. All right, so distance means that we don't care about the direction, right? So this one, especially now that we have the graph made, it's pretty straightforward. All we got to do here is just go, well, it's 8 up and down, right? You went 8 from there to there. And then we had to go, like in this section here, we know that we went down 8. But again, I don't care about the direction, so this is just 8 plus 8. And then from there, we knew that we went up what was it, 40. Okay, well, that's just 8 plus 8 plus 40 is equal to 56 meters. Now, if you didn't have the graph and a bit more mathy, we could do these in sections, right? Where we could say from a time equal to 0 to a time of 1, then it would really be the absolute value of s of 1 minus s of 0. I'll explain what this means in a second. Okay? And then, which would be equal to the absolute value of 8 minus 0, which is equal to 8. Okay, what I did there was really just figuring out the distance from here to here, right? The up and down. We just went our height, right? S of 1 was how high you were here, minus S of 0, which was your beginning, which was just 8. And the reason why it was the absolute values is because I don't care about the direction, right? In this case, the absolute values didn't matter. It would have been the same either way. But in the next one, if we go from an interval of t at 1 second to t at 3 seconds, then that would be s of 3 minus s of 1, absolute value bars, which ends up being 0 minus 8, right? Because that's this height minus this height, which comes out as a negative number. But I didn't really want it to be a negative number because I don't care about the direction, right? So this would be 8 again. Okay? And then the last one for the last section, t3 to t of 5, or t is equal to 5, then that's going to be s of 5 minus s of 3, absolute value, which is equal to absolute value of 40 minus 0, which is equal to 40. And then we'd add them all up, right? So, but we just knew that from the graph, right? We could just kind of see that. All right, moving on to acceleration. So with acceleration, you've probably seen where we're going with this. Acceleration would just be the derivative of the velocity. Now, let's look at an example to see how this makes sense. So if we had like a distance time graph, and maybe we'll do the example like we did above there. So this would be an example of like throwing something up in the air, right? So it has a velocity, certain velocity, like a positive velocity to begin with, then comes to a stop at the top, right at the peak, and then has, negative velocity down here, right? Okay, so if we figured out the velocity time graph of that same situation, which would just be the derivative of the distance time function, so velocity time. So this is velocity time now. How does that look, right? So if you took the derivative here, right, you've got a positive number. Okay, so you've got a positive number to begin with. And then here you've got a derivative of 0, right? So velocity of 0, so that'd be here. Okay, just lining up, right? Because the times would be the same. And then here you've got, well, like the same velocity, but in the negative direction, so like down here. So maybe this looks familiar from physics. Now, that's a straight line, right? Nope, shoot. Anyway, you get that should be a straight line. Okay, so then if I figured out the slope on this graph, what was that? Well, in this case, it'd be negative 9.81, wouldn't it? It's the acceleration. It's the acceleration of this object. Okay, which is the slope of this object. So if I take the derivative of this, then I'm going to get the acceleration, right? Now this was a simple example because the slope is the same all the way everywhere, right? So it gets a little bit harder to think about when it's a cubic function, right? So if you get a cubic function, and then this one to be a parabola, right? And then it goes down from there. But that's the idea, that it's going to be your slope on a velocity time graph that gives you your acceleration. Okay, now, yeah, that's pretty much what we just said here, right? Acceleration is your derivative of your velocity. You can also say now that it's the second derivative of your position time graph, right? So 2 ticks. So that's one way of writing it. Or in Leibniz notation, a little bit strange, it's a is equal to dv over dt, or d squared s over dt squared, right? This is saying the second derivative. All right, number 5 example. On the moon, an object is dropped into a crater 150 meters deep. The height of the object from the bottom of the crater is given by that function, where t is the time in seconds and h is the height in meters. Determine the velocity and acceleration of the object at t seconds. So just general formula. All right, so then the velocity of this would just be, so velocity is equal to h prime, the derivative of h, which is equal to negative 1.6t. Okay? And then the acceleration, which would really just be h double prime, which would also be equal to just v prime, the derivative of v, which is equal to negative 1.6. Just taking the derivative of that, right? So now what's the acceleration due to gravity on the moon? Well, we just figured it out, right? It's going to be 1.6 meters per second squared, and then it would be always directed toward the moon. All right, next one. The position function, s of t, of a particle moving in a straight line is defined by the equation this, where s is the position in meters and t is the time in seconds. Determine the velocity and acceleration of the particle at t seconds. All right, so same thing really, right? So this would be v, which is equal to, and I'll use Leibniz notation this time, ds dt, which would be equal to, and then that would just be 16t minus 4t squared. And then the acceleration. So the acceleration, which you could also say was d squared s over dt squared, is equal to just 16 minus 8t. All right. Determine the instantaneous acceleration at t is equal to 1 second and 4 seconds. So we'll say, okay, so a of 1. Right, so that'd be the acceleration at 1 second, will be 16 minus 8 times 1, which is 8 meters per second squared. And a of 4 would be 16 minus 8 times 4, which is equal to negative 16 meters per second squared. Now, this might be a good time to remind you about what positive and negative accelerations mean, right? This positive 8 meters per second squared doesn't necessarily mean that it's moving in the positive direction, right? Think of it more like the direction that the force is pushing, right? So this particle, let's give you an example. Maybe this particle was moving to the left, right? Maybe it was moving in the negative direction, and at this point, at 1 second, this 8 meters per second squared, that means that it's accelerating this way. And if you remember, that can happen, right? If an object is moving in the negative direction, that would just mean that it's slowing down, right? If it was moving this way, but accelerating this way, that means the object is on its way to stopping, right? And then it would stop, and then eventually it would start accelerating back that way again, right? In the positive direction. Okay, so positive accelerations don't mean it's moving in the positive direction necessarily, right? Same with the negative direction. We just know that the force, it's like the force pushing on the particle is in the positive direction, and the force pushing on the particle here is in the negative direction. Okay. What is the maximum velocity of the particle, and when does it occur? Okay, so if we think about this, right? So let's say we've got some particle that is speeding up, right? So it's going this way. So you can imagine that your slope is getting steeper and steeper, right? And your your slope being your speed, right? So the steeper and steeper the slope is as it's moving this way. And then something's going to happen and it's going to turn around, right? It starts going the other way. Right there, right? That would be your maximum speed, wouldn't it? Right where it's going from an area of increase to an area of decrease. Sorry, rather, let's say where the slope is increasing and then the slope is decreasing there, right? So we know this as an inflection point. And where do inflection points happen? Well, they're going to happen when the acceleration, when the second derivative is equal to 0. Okay? So we can say that 0, this is going to happen when a is equal to 0, when the acceleration is equal to 0. Now, we've seen this before, too, in Physics 20, where, do you remember the pendulum one? And when it was swinging, right? And we had to figure out where the pendulum was the fastest. And that was also the case, right? When it was right in the middle, right? When the restoring force was 0, when the acceleration was 0, that's when it was moving the fastest. And in our situation here with this particle going back and forth, it's actually kind of similar. You've got this particle that's like moving this way and then it's moving that way, and it seems like it's going to keep going back and forth. There's like two opposing forces happening, is what would be happening there. But that's the same thing, right? So it's not a new concept that a equals 0 would be where your maximum velocity would be, right? So anyway, so that's the idea. So when a is equal to 0, that'll be our maximum velocity. That would also be, right, if you were graphing, well, no, maybe I won't get into it. I think I've explained that enough. Okay, so when a is equal to 0, so we'll say 0 is equal to, and then the acceleration formula, so 16 minus 8t. So then 8t is equal to 16, so t is equal to 2 seconds. Okay, well that helped me figure out when this is going to happen. But the question said, what is the maximum velocity? All right, so if I know when, I have the tools to do this. We can say the velocity at 2 seconds is when that is how we figure this out, right? So we need our velocity formula. So 16, here I'll just do this first. V is equal to 16t minus 4t squared, and then I'll sub in v of 2 for 2 seconds. So 16 times 2 minus 4 times 2 squared. So v of 2 is 16 meters per second. All right, last one. Determine the times where the acceleration is positive, so a is greater than 0, and negative when a is less than 0. So let's throw down the number line. Whoop. And let's figure out when a is equal to 0. Okay? So we'll say 0 is equal to, and then the function for acceleration. So that was 16 minus, oh, that's not a minus. 16 minus 8t, all right, to find our critical numbers there. So our critical number there is, well, the one we had right there too, which makes sense, right? So that's going to be at a time of 2 seconds. Okay, so that's going to be point of interest here. So 2 seconds. And then we also started at a time of 0, so I can throw that down. And then we really just need to throw some numbers into that, right? So if this is our acceleration formula, is a is equal to 16 minus 8t. Okay, then let's throw in 1, right? So if I throw 1 into that, then that's coming out positive. Okay, so your acceleration is going to be coming out positive in that section. And then if this was 3, then that's coming out negative. There you go. So that's probably good enough, but we could say, we also do it right and say that a is greater than 0 when t is greater than or equal to 0 seconds and less than 2 seconds. A is less than 0 or negative, where t is greater than 2 seconds. We also could have done this in interval notation. I was just changing it up on you, just because. So that's it.